My name is Rahul, and I'm an engineer on the Android Toolkit team. I work on Android X performance, and these days I focus a lot on baseline profiles. Today we'll look at how to make apps predictably fast using baseline profiles. Let's hope this works. Right. The goal is to make your app a lot faster, dramatically faster with baseline profiles. So, with the risk of sounding like an infomercial, I'm going to make the claim that you can make your app at least 30 to 40% faster in about an afternoon's worth of work. And if that doesn't work, you can always complain on Twitter. So to understand why they're so effective and how they work under the hood, we need to establish some common vocabulary on all the optimizations and tricks that Art has up its sleeve to make your app run faster. So we look at app compilation, app launch, and all the moving parts that Android has. So we look at app compilation first. This is something we do day in and day out as Android developers. We look at what happens under the hood for application launch and installation. We look at state-of-the-art circa 2018, which was cloud profiles. Then we look at what baseline profiles are and how they improve on cloud profiles. And finally, we look at what's the state of tooling and how to generate and use these baseline profiles for your app. And then we look at some case studies from Maps and Play. So let's look at app compilation first. This should be easy. We do this every day. We start off with some Java or Kotlin code as Android developers. We feed it into Java C or Kotlin C, which is the compiler that converts Java code to jar files or Android archives. We look at a list of transitive dependencies, and then we merge them and we feed it to R8. And the goal is to have some optimizations run before the app even reaches the user's device. Because the less code you ship, the less of it needs to be optimized, the less that the runtime has to do. So R8 has a lot of tricks like dead code elimination. It inlines a bunch of methods to speed up things, and it rewrites some code to make your app faster. And then finally, we use D8 to convert the Java bytecode to DEX code. And the DEX code is the lingua franca for the Android platform. Everything, what the platform understands is DEX. And then we'll zip it up together. We'll give it a manifest. We'll throw in some resources and assets, and here you have your APK. So now we have successfully built an APK that we can ship to production. Now let's look at what happens afterwards. Like, how does your APK end up on a user's device? So typically, the user downloads the APK from Google Play. The Play client will download the APK and hand it off to package installer, which is a platform component, and it knows. It does all the bookkeeping, provisions the APK on the user's device, and sends a package changed intent to the platform. Usually the launcher responds to it, looks at all the packages that have changed, and then figures out what the launcher intent is for the newly installed APK, makes the icon available on the launcher. So these are all the things that happen even before your application is launched. And finally, now that we have an icon on the launcher, the user can click on it, and then this results in a Zygote fork. Zygote is essentially gives you a reference to a class loader, which gives access to all the framework classes. So typically, this is the Android framework code that your application is linking against. So anytime you link against app.context or activity or something like that, these are all classes that are being loaded by the system class loader, which is ready to go even before your application asked for it. So the Android runtime essentially forks an existing process where all these classes are preloaded, and it creates that fork, and you get the benefits of it. Then we can load your APK. So this is where we load your manifest, we load your assets. We figure out what the default activity is that can launch to the launcher intent. And then at that point, we can, here I'm using a vague box called execution. So this is where the runtime has a couple of tricks up its sleeve where it sets up things like just-in-time compilation and other things that I'll talk about later. Finally, we've discovered your entry point activity. We know the component factory that's being used by the APK. Then the platform can invoke the component factory, initialize your activity, and call on start. So I basically call application on create and subsequently activity on start. So all of these happen at app launch time. And so let's look at that box, which I left vague as app execution, right? So pre-Froyo, there's not much going on. There's your DEX code is loaded from storage. The Android runtime just interpreted that code, and that was it. Interpretation was typically slower because there's the runtime that's actually executing instructions step by step, and there's a state machine involved. So it's not typically super fast. Come Froyo, we introduced a just-in-time compiler. So this is where the runtime figured out the hotspots in your application and the critical parts in your application and said, oh, rather than interpret them every single time, what if I pre-compile some of them or compile them dynamically and held onto the compiled code, and then subsequent invocations of that code would become much faster. So your application would see speed up. So your app would start off slow, but over time it would get faster. So involved in better user experience. And then come Lollipop and Marshmallow, the runtime said, oh, what if we just did that for all the app, for the entire app? What if we fully ahead of time compiled the application and generated something that we call optimized DEX files called ODEXs? So typically what happens is the application gets installed, and under the hood there is a new compiler that's on every Android phone. It's called DEX to OT. So we'll convert DEX files to OT files or ODEX files. And that's the optimized bytecode, or that's the optimized machine code that Art can then load to install to run your application. Now, this compiler is not great because it's typically very slow. Imagine shipping a compiler on a phone that ran Marshmallow. It's not very fast. So this meant longer install times. And also, because this was basically compiling the entire application, and not just the important parts, it would generate a lot of unnecessary code, unnecessary from the point of view of the user, because there are seldom used features in the app that the user would not even typically see if we end up compiling them, and they involve wasted resources. So what if, so that's a huge problem. On the other hand, once the application was compiled, we had ODEX files for the entire application, and app launches and interactions that were typically very fast because they're all optimized already. So that helped. It also gave you the famous optimized apps dialog. So every time the platform under the hood had some improvements, we had to recompile your DEX files to generate OT files, because we introduced more and more optimizations as Art improved under the hood, and this really annoyed users because all they wanted was use the app. They wanted to use the app, and we were actively preventing them from doing so by showing them this every Android update, right? So it's very frustrating. Also, as apps got bigger, this process got even slower because you're shipping more code, the more code needs to be optimized. So it went from being super slow to not scalable. So we had to figure out a better way. So in Nougat, we introduced something called profile guided optimization. So rather than optimize your entire APK, the application starts off in interpreted mode and with a just-in-time compiler like before. But while the just-in-time compiler is running, it essentially records all the critical sections of your application and dumps them into something called a profile. And at some point in time, once the device goes idle, there is a process that Art uses job scheduler under the hood, and it runs something called background DEXopt. And background DEXopt is essentially looking for current profiles, and current profiles is kind of a staging directory of things that need optimization. So there's this job that looks at all the applications that have current profiles. It looks at them, it converts them to ODEX files. It basically takes only the critical sections of the application, and then it commits them to reference profiles, and essentially truncates current profiles in order to mark the transaction as done. So this happens over and over again. So once the application is optimized, subsequent launches see the ODEX files instead of starting in interpreted mode, because we've compiled those critical sections already. And so in the beginning, app starts up slow, but once Art figures out the critical sections, and then and background DEXopt has run, apps get faster. So now this process repeats itself, and it's kind of a continuous feedback loop, because as the user uses your app more and more, the runtime has a chance to discover new hot paths and basically keeps dumping that information in the profile. And subsequent iterations of background DEXopt will pick it up and add it to the ODEX file. So apps get faster, and this kind of responds to what the user tends to do with the app. It's responding to what the user's intent is too. So if an app is only using some screens, only those screens need optimization. We don't need to optimize the entire app. I've used the word profile a couple of times already, so let me define it formally. it's just a list of classes and methods from Art's perspective that need optimization. So we just need to compile those bits from bytecode to machine code. And as I said before, if you look at the performance characteristics, performance starts off not so great, and then as Art has more information about your application and has a chance to run background xop, it gets better over time, and then the user is happier as a result. So, but you might be wondering, it's not great that we start off bad, right? So this gives us an opportunity to improve the state of the art. In 2018, we called this initiative Cloud Profiles. So if you look at this chart, and you might be wondering, why do we have to regenerate this profile for every single user that's using that app, right? What if there was a way of crowdsourcing this information? So what if we could just take advantage of the first few slow starts from a cohort of users, and we uploaded that information to Play, and then we aggregated that information, and subsequent installs could just bootstrap that profile as a starting point and then improve on that. So what happens as a result is apps tend to get faster from the start, from the get-go for the second cohort of users. That's exactly what profile aggregation is. So what happens is your application gets installed for the first set of users. We build reference profiles. Those profiles are uploaded to Play. These profiles are essentially Art implementation detail. They're SDK version specific and typically sometimes specific to a device type if the OEM made changes to the runtime, for example. So these profiles are captured on a per SDK and on a per device type basis. So you might end up in a situation where if you have a cohort of users that are using one device type more than the others, that device type will get preferential treatment for profile aggregation. Now, unfortunate bit is this process takes like weeks of time because it takes us that much time to generate a representative profile. It's not enough to just take the first few app launches because that may not be representative. What if it was just your application performing some background work using Job Scheduler, for example, and not showing any activities? So it's not enough if we take the first few profiles and then call that a reference profile. We also need to wait for some level of confidence before we can say, yeah, this is a good-looking profile. This is good enough. And then once we have enough of these reference profiles, we zip them up and we basically keep track of them as additional metadata that's corresponding to that APK version. So those profiles are, again, specific to versions of your APK. So as APK versions evolve, we need to start over again from scratch because we know that code paths may have changed in the new version of your APK. So all that information is tracked in a payload that we call dex metadata because it's just metadata corresponding to your application. Now, once we have this dex metadata, what do we do? How do we take advantage of this, right? So if you look at the previous app install flow, rather than just downloading the APK, we will download the APK plus dex metadata when available, and then we'll hand off two pieces of information instead of one to package installer. And what package installer does under the hood is it knows that dex metadata is a good signal and it's a representative subset of the app that can be optimized very quickly. So it runs dex to oat right away at install time, and rather than having to do background xop that takes effect after a day or two, this takes effect prior to the user even launching the app. So the app gets really good performance to boot, which is good. Now, we've solved one problem, but we've introduced another problem, right? We have this cloud profile performance characteristics where things start off slow because your first cohort of users don't have any profiles, but as they're building the profile and building a reference profile, and as they're uploading that information to Google Play, things get better. So performance gets better over time, and then the application developer decides to update their APK and then ships a new version. And then we have to start over again. So we have this reset in performance. So if you've noticed like spikes in performance and if you've noticed jagged lines in console, it's not you, it's actually our fault. And we were not transparent enough about it, but I hope this sheds some light on like what was going on and why your apps just got magically faster. So now another interesting thing is as application development velocity improves, there's a chance that cloud profiles never take effect. So, for example, one of our internal apps, Maps, decided to change to a weekly release schedule. And for an application like Maps' install size, it typically takes around a week to generate a profile. That meant like users would never see a profile, so performance was always like really bad, and so that was unacceptable. So they were like, okay, this improves some things, but it introduces other problems. So at this point, you have all the context that you need for baseline profiles. So now we introduce the next improvement. So essentially, what if we ask the developer to tell us what the critical sections of the code are, right? Like why do the guesswork? Why run apps on user devices? Figure out all this information and like how about being a lot less magical about it and say, hey, developer, if you know what the hot paths are, just give it to us. And so essentially, a baseline profile is just a list of classes and methods that we need to optimize. So that's something you can provide. Importantly, they can be defined by both libraries and application developers. And so it's important for libraries to be able to define them because as we move to a more unbundled world, so like, for example, Jetpack Compose is a huge initiative, right? We're unbundling the entire UI toolkit. And by unbundling, I mean it's no longer shipping with the platform. It's no longer part of the system image. So it does not get any preferential treatments like full ahead of time compilation or being a part of the zygote, because now we can't be on the zygote process. All this new code is being loaded from the app side, so things are not as great from the application's perspective. So we need to be able to define these rules and bake them into libraries, so even if the application developer did nothing, they would still reap the benefits of baseline profiles. So the good news is, even if you just use the latest versions of Jetpack libraries or Compose or other third-party libraries, there is a provision in which they can package baseline profiles as part of the library, and they all get merged subsequently, which is nice. And when you're providing these list of rules, they're typically human readable, but then they're eventually compiled to a binary payload because we want the APK size footprint to be as small as possible. We don't want to regress on that because we want to keep the download size small. And then these still participate in profile aggregation. So it gives you a good baseline performance, but then we can still improve on that using the same cloud profile pipeline, right? So these typically bootstrap the cloud profile pipeline. So you're always starting off with a baseline profile, and then you're working your way, so things get better from there. So the goal is to change this graph and to make it flat, essentially. So you always get predictably good performance, even if you're shipping every day or even if you have a crazy release schedule. So how do we take advantage of this? So libraries can define rules in a human-readable format in a file called baselineprofile.txt. It lives alongside source main Android manifest.xml. So wherever you typically find your Android manifest.xml, there should be another file called baselineprof.txt. The rules look like this. They're human-readable, but not meant to be written by hand. So if there's one thing to remember, please don't write these rules by hand. You will have a bad time. They follow the JVM descriptor syntax. There's a few flags in orange. P stands for post-startup. L is just a class descriptor. HSP just means hot, important for startup, and important for post-startup. So it's important for all three categories. L just means it's a class that's important enough that it needs to be preloaded during app launch. So there's just some descriptors that we use. And then AGP ships with a special compiler called profgen, which converts the human-readable format, merges them, and then builds the compact binary representation. So AGP takes the human-readable format, the APK, the release APK, and an obfuscation map. Because if you're using R8 and you're obfuscating your APK, we need to know how the symbols map from the source symbols to the obfuscated map, to the obfuscated symbol, so we can rewrite the rules in the binary profile to match your eventual APK. And so what you end up is an APK with some baseline profile plus a bunch of metadata. Why do you need the metadata? So as I said, baseline profiles are tied to the version of the SDK or tied to the version of the operating system, and they can evolve as art bakes in more information to profiles, and so it's free to change. So the profile that we bake into the APK targets Android P. Android P through R use the same profile version. Android S used a new profile version, and every version prior used a different profile version. Now, this is additional complexity that we don't want developers to deal with, right? We bake in the P profile plus enough metadata so we can go back and forth to any target SDK platform. So all that complexity we manage under the hood, so you don't have to. And so let's look at the build process, right? So rules can be defined by both applications and libraries. And so once the jar files get merged and fed it, and you have a procard rules.profile, R8 can do its tree shaking. It produces an obfuscation map. And at that point, you can use, so once you have Dexer that produces the Dex files, you can essentially merge all the human readable profile rules. You can make one canonical file that has all the rules, and then you can pass in these three inputs, like I said. So you have the mapping file, you have the eventual Dex file, and you have the rules, and then we can build the APK with the profile information. So that's how these files get packaged into the APK. And now, okay, now you've built an APK with these profiles. What happens next? What do we do under the hood to make these profiles available through the distribution channels that we have, right? So once your APK gets published, this APK is, as it flows through the publish pipeline that's internal to Play, we detect that the APK has these profiles embedded in them. And so what happens under the hood is we will extract them and we'll transcode them to every target platform version where a request can come from to download the APK. So we'll try and support P through whatever the latest version of the platform is, and we'll have a version profile that can target, or we'll have a profile that can target the corresponding SDK version. So it depends on where the download request came from. We know exactly which profile to map and then download alongside the APK. So what happens then is when the app is being installed, the Play client will download and ask for this bundled payload like it did before with the cloud profile pipeline, where we could provision Dex metadata. Instead of having an aggregated profile, here it'll have a baseline profile. And then we can just hand that off to package installer like before, and then your app gets optimized prior to first run. So that's nice. And you get ODexes to boot. Now, all this is great, but if I have to test, if this was the only way to test my app with baseline profiles, it was kind of flunky, right? You have to publish an APK and you have no idea if you did things correctly. So to give you a faster feedback loop and to help devices that don't have full support for cloud profiles. So cloud profiles came circa Android P, but Android N, actually starting Android N and O, we had profile guided optimization without the package installer support for Dex metadata. So we still did profile guided optimizations, but we wouldn't upload those profiles. Package installer did not know how to take advantage of those profiles. But profile installer solves that problem. So essentially what profile installer does is it supports devices that don't have the full cloud profile pipeline, like essentially Nougat and Oreo. It also supports devices that don't have Play support because you may be running your app on other devices. And it also supports local profiling and benchmarking. It's kind of important because this is the canonical way for you to measure the before and after with baseline profiles. This is the only way you can tell things are working locally. And the way this works is if you revisit DexOpt, right? So the just-in-time compiler records things into a current profile. They get picked up by background DexOpt. Things move to a reference profile, and that loop repeats over and over again, and we build a better and better reference profile. Essentially, what profile installer does, it just drops your profile in a location that Art expects to find the profile in Android N and O. So it's like a nice little hack, but it works. And so the Art runtime does not know the difference between a profile that the just-in-time compiler wrote or a profile that the app wrote on the compiler's behalf. So we just drop the profile, it gets picked up by the background DexOpt process, and it just works like it did before. So we take advantage of the same primitives in the platform on N and O, but we still make it work, and it's our responsibility. So all you need to do here is just declare a dependency on profile installer, and we'll do the right thing. The only difference is, unlike cloud profiles where the optimizations kick in during install, even before first launch, this happens on first launch. So that's the key difference. And the just-in-time compiler can keep adding things to the profile like it did before, and so it forms a good baseline, but things can improve over time. So, and once post DexOpt, the app gets predictable performance to boot. And now, so I've given you like a lot of theory, and I've told you how things should work, but like how do we take advantage of all this, and what are the tools, right? So let's look at that. So the most important thing for baseline profiles is you need good rules. Rules will dictate how art can optimize your APK, or how art can optimize your code. And so you should really strive to cover critical user journeys. So these are important for your application. These are typically important bits of UI. So if you're a shopping app, this would typically be your like launch page, or where adding to cart page, which is really important for your business, for example. And you will use macro benchmarks as much as you can to guide how these profiles are generated. So macro benchmark ships with a very cool test rule called baseline profile rule, where you can essentially code up what a typical user would do when using your app, and then macro benchmarks will run that scenario over and over again, make sure that the compiler and the caches are warmed up, and it'll dump a profile that is viable, that would have been the ideal profile for that scenario. And that's how you generate a baseline profile. And then a corresponding JUnit rule that you can use to measure the difference between uncompiled and compiled states is the macro benchmark rule. So let's look at a case study. Here we will use the Now an Android app, which is available on GitHub. We'll write some code to generate a baseline profile. So first, as I said before, we'll declare the JUnit test rule, which is the baseline profile rule, and we'll write a JUnit test. Here we'll say we want to collect a baseline profile for this package name, which is Now an Android, and we'll just code in our user flow. So what we're doing here, we'll start activity and wait, and then we'll just wait for the main looper to be idle for a bit. So we'll wait for the application to settle down. And once we do that, we're waiting for the interests tab to be available on the application. And we'll click on it. And that's the critical user flow that we're targeting. And we want to make sure that this bit of the application is optimized for Now in Android. At the end of the day, when you run this in Studio, it'll spit out this file that you can copy and drop in source main. So this is basically all the rules that are ideal for that scenario. And then once you build with a new enough version of AGP and you analyze your APK, you will notice these two files in your assets and desktop folder. So you will see there's the baseline.prof file and a prof.m file, which is the profile targeting P and the corresponding metadata that we need to move to target other versions of Android. And now you've generated a profile. The profiles are baked into the APK. How do we measure the effectiveness of it? Like how do I get those numbers to say, hey, I improved by this much? For that, we'll similarly just write, so we'll do the exact same thing like we did before. And instead of baseline profile rule that generated the baseline profile, we'll use the macro benchmark rule to measure. And here I'll write a startup utility that takes in a compilation mode, and I'll talk about what compilation mode is in more detail. And then we'll just write a measure repeated loop. So we'll say I want to measure Now in Android. I'm looking for startup timing, which is time to first frame and time to report fully drawn. And then I'm using the compilation mode that came in. I'll run the scenario for 10 iterations, and I'll use the cold start. I'm interested in measuring cold start numbers because I want the process to always start in an uncached state and the process to be like not alive before. So I'm not interested in measuring warm starts or hot starts where the process is up and the activity is up. What I'm trying to measure is cold. And I always want to start on the launcher. So I always use my setup block to go home, and I'll use the default intent to launch the application. So I'll just call start activity and wait. And here I can do a lot more. I can, just like I did before, I can just wait for the interest screen to be available as well. But for the purpose of the demo, I'm just keeping things simple. And so now that I have that helper, I just need to define two tests where I'll pass in two compilation modes. None essentially means there's app starts off in an uncompiled state, and partial means that we are using a baseline profile, so we have partial compilation. And once you have that, you get these numbers in Studio, and you can see even for such a simple use case, we improved performance quite dramatically by 60 milliseconds for app startup, which is pretty neat. And you can do a lot more if your application is more complicated or you're testing something that a real user would do. It actually makes a huge difference. And so I just told you that all we have are profiles targeting P, But how do we actually like bootstrap this profile locally for measurement, right? What is macro benchmark doing under the hood? For that, what we have is we have a special broadcast receiver and profile installer that macro benchmark uses to bootstrap the profile like it did for NNO for local development. So it writes that information to the current profile, and then we'll kill the process because we always want to start the benchmark in a cold state, right? Because that's important. I don't want the process to be up. Sending a broadcast to the app basically wakes up the app, so I just need to restore the state by killing the app again. And then macro benchmark kicks off something called a speed compile, which is an invocation that Art will respect to invoke dexopt right away, and it builds a reference profile and an ODEX file even before the start of the benchmark. So that's how we can put the application in the right compile state. And profile installer, when it writes to the current profile, it's doing the same extraction and transcoding that would happen on the server side pipeline when we published the dex metadata like you saw before. So we're doing all the heavy lifting to make sure it's super easy for you to test this stuff. And then once you have the ODEX files, you can and the app is in the right compile state, you can then benchmark the effectiveness of that set profile. So now I showed you some code. Let's look at some interesting case studies. So so Maps was one of our first partners. We tried baseline profiles with Maps, and you can see that performance is clearly dramatically better. You can clearly see the visual difference. This has not been sped up in any meaningful way. So Maps starts 30% faster. It actually improved business metrics a lot as well. It caused people to search 2.5% more. And that might seem like a small number, but remember, Maps is a very, very large application. Like even a 1% shift in anything is pretty significant. And this is probably the most significant improvement Maps has made in cold start for a while. So this is unlocked by baseline profiles. Remember that performance characteristics curve that I showed where the app starts off poorly and it gets better over time. Notice when on version 10.7.8, when Maps switched to baseline profiles, things got a lot flatter. So it no longer started off worse and get better. It actually started off pretty well and stayed there. And it was like a nice visual confirmation that everything was working the way we thought it should. And this is a more interesting example because it uses Compose. Play used Compose from the very early days, and they were another partner who were helping us test baseline profiles across several different Android SDK versions, and Play starts off 40% faster. So again, this video has not been sped up in any meaningful way. It significantly makes that kind of a difference. And yeah, so I have some takeaways. A lot of this is bleeding edge. So we've kept making improvements along the way. We've kept making changes to AGP to make things as simple as possible. So if you remember, just remember these things. Just use 7.3 RC1 or newer, and use the latest version of Profile Installer and macro benchmarks. It will make your life a lot easier when you're trying to use these things. And also remember to use the latest version of Jetpack libraries and Compose. So because we package baseline profiles in libraries now, even if you just did nothing, you still take advantage of most of the pipeline. And we are adding profiles to other third-party libraries like Retrofit, OKIO, and Lottie. So like all of those libraries are also shipping with baseline profiles. Some additional resources. So performance is a good landing page for all performance-related things that we're working on. So baseline profiles and macro benchmarks are your best tools in this journey. And thank you. Yeah.